We covered the spanning tree. We also talked about this importance of minimal spanning tree, right? Then after that, there is a two algorithm give us to finding the minimum spanning tree, which is that Kruskal and the Prima, right? And then, of course, the two algorithm has, from the performance perspective, is same, and that, but there is a applying the two different algorithm has a different situation. One's that, of course, very distinct difference Kruskal has can apply in the two different graph, but Prima cannot do this. This is a kind of difference. And then, of course, they have a different kind of philosophy, starting point, right? One is that continuously finding, and then Prima is continuously finding the spanning tree, but Kruskal's, they starting first at the minimal cost, then they continuously who's next, but it's uh, not concerning the continuously. So it's a difference, right? But how we can implement in the coding level, how we can, let's start first the Kruskal, right? Then there's a two things very important in the Kruskal. Let's define this. Let's start first the uh, graph. The graph is, let's say, they have a four vertex, 0 to 2, 0 to 1, 0 to 2, 0 to 3. They have, of course, 0 to 2's weight is 10, 0 to 3's weight is 5, 1 to 3 is 15, and then 1 to, you would say like this, okay. Um, okay, should be fine. Okay. I mean, 1 to 3 is 5. What, like this? 1 to 3 is 5. 2 to 3 is 4. 1 to 2 is 6. Okay, that's a kind of the same time concerning the weight. So how about such a graph? We needed to, create such graph. Pause, you know, edge and the, adding the edge, which is that we already studied in the creating the graph, right? So you remember how to DSF, BFS, right? BFS. So that's you can generating the age, of course, but very important is how we can, using the Kruskal to finding the, finding the minimal spanning tree, right? Now, there is a two things, of course, very important. First of all, they needed to sort it, because what's the sorting is, why is concerning sorting is because uh, they trying to get this minimum one first. If I sort it, I know where it's starting from. So if I sort it, I can start from the minimum. Minimum is the first one, of course. Then the second one is I have to avoid. When I already stored all of the age, then I can take that which one is the smaller weight. Then I can start from that. The second one is how to make sure that this is not been cyclic, right? So second thing that we also use that the detected cyclic unit, which is that, of course, the algorithm actually two-way. One is using the parent. Parent. Okay, let me think about it. Parent. Parent root. Okay. I mean, what does it means? What does means is okay. Let me also. This is also important to. Maybe I can. I mean, just draw the very short graph to explain why is it important to, you know, uh, there is a two way you can find avoid cyclic. Uh, how we can avoid cyclic if we when we create, of course it's a that's the simple word avoiding cyclic, but how we can avoid, right? This is big deal. The if you remember this, you can did lab 10. Of course that's a little bit, you already start this warm up this how to doing the cyclic. So can you give me an idea how to detect cyclic? Hmm? Right. This is one way, right? So it means then I needed to, I mean, okay, that's not, I mean, if there is a repeat two times, it means they become cyclic, right? So that's one way. They trying to storing the but if you remember the one edge has two node, right? So either one the same time you need concerning the edge should be is minimum. Okay, two things. So you needed to using that there is a if you give this to one age, the first you need to choose one is a small weight, then you have a choice to two node, then two node should be in if you can try to link it, then but you should know this two node should be do any kind of extension, then finally you make this cyclic. So it's important that you can even you can choose this weight, you can distinguish, you can identify this is a small weight, but after that you can able to access the two node, then you need to check it this node should be already existed in the I mean uh, in the array. It means you already have, it means okay the next time we can make this become the cycle. That's one way. Uh, another is that if it is the because those are linked together, then one should be as a father. I mean, another should be you can count it as a child. I mean, there is a one algorithm being called if there is a subchild, also recognize the super father. I mean, they make this, they didn't directly count it as the father, but they only I mean, recognize only the count it as a super father. It is only the one father. It means that's also that easier to detect it. This is has a same link. If there is a same link existed in the other link, but finally there should be, it means if there has a same father, okay, it means this is, you already have a extended, then in you belong to one cycle. Now you can check it, this has not been visit, then you can able to link it. The just linked it fathers, not any others. That's another idea. In order to get this idea, I recommended two article. I mean, this is one article that disjoint unit by rank by pass. This is one, and then another one to using the union find approach. There's a two way you can using the I mean avoiding the cyclic approach. So either the one is both should be fine. Okay, both should be fine. In our case, we used it. Yeah, in our case, we used it. Uh, we used it parent rank. What's the rank means? Okay, what's the rank means? The 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 height of the tree. Do you remember what's the height? Right? I mean, so you can think that the rank is height. I mean, at the first they also. I mean, at the first you can. At the first you can give this value and the parent is -1 and then rank is 1. Okay, both you maintain this two array. One is you can store in the parent. Another, what's the parent means super father. I mean, it's both as children of sub children's not directly recognize the fathers, but they storing the who's the super father. So those should be has to make this easier to you can distinguish it. So at the first, all this that by default is -1. So if you use the -1, they okay, this is the first visiting. Okay, then it's 1. It means also the first time you accessing. Okay, so what you're doing is there's a two important functions: find and union. Find is trying to find who's the father. Okay, now for example, if you give the one index, then they will be, if this -1, okay, that means okay, it's the first time. There is no any kind of, we recognize that there is no any kind of sub children existed, so just directly return to index. If not the -1, it means okay, there has had something already been linked it. The result of from unit. Unit is make this two node join together. Okay, so if you unit is make this link together, they not be becoming the -1. So at that time, you have to find it. What's the next of your parent? Then they will be give this index of the parent. Then they will be update this parent. So finally, they found the super father. Okay. So that's the find. I mean, what's unit doing is actually, if it is the, of course, you give the two vertex. One is x, one is y. One you can think that's x is source, y is destination. If you remember the the DSF or BFS, there is a talked about that we from the link, I mean, destination and the source, right? So you can think that this X is source or Y is destination. That should be fine to you can make the formalize this information. So S1, S2 is not same. It means it's kind of not been linked it before. Okay, if it is the, I mean, of course they find it. This is a make sure they found it super father. The second one also find it the super father. I mean, if it is the same, it means okay, there has already been linked it. Okay, already been linked it is come here. Okay, then they okay. It is if it is the if it is the same, it means what does same is at the first is first time same, right? First time is both. I mean, S and I's had each of the has index, right? Index is same as there's father same. I mean, if it is father same, we can add it. Okay, we had the same fathers. I can add it with the another link. That should be make sense. I mean, there's a 1 to 2 and then 2 to 3. That should be like this. I mean, 1 to 2, 2 to 3. It's one is linked, then another is it's another link, right? So they come to the, if there is a same father, then they will be linked together. Then at that time, they beginning to extend it. They already make it extended, so that's the reason you need to add it. This is a second one is a sub. I mean, how to say sub tree. So that's the reason you needed to add it the sub tree with the original and the first tree. You become the longer tree. Okay, so that's the reason. I mean, that's the reason the S1 had a little bit longer height. In other words, a longer rank. Okay, doesn't matter. You call it the rank as height, same. So this is the reason you just added update this. I mean, the parent link. I mean, this one, what does means is they had added one subtree to another subtree. Okay, if it is not the same, okay, if it is not the same, of course, they doesn't have a same, doesn't have the same, it means there is a problem of actually it's not the problem, the concerning that the performance, actually they're concerning the performance in order to let you understand what is from the performances. Actually, you need to read this article, and then here's what is the idea. Here's okay, this one. You need to able to continuously add one. For example, let's say the 4 to 2, 0 to 1, right? I mean, you can continuously add it. There's another child continuously, as long as they didn't make the cycle. That should be fine. But the problem is the recursive problem they had. I mean, how about if, I mean, in order to add, for example, I'm checking this one, the final I have to find this one, then 0, then 0, then 1, then final I did the end of the position. How about if I just do it once? If because I'm either the 1 and 0 and 2 has the same superfather. If they has a superfather, how about I can directly add it to superfather? It should be same. Okay, so that's also didn't make this direct cycle. So that's the reason they had choice that make this picture like this. Okay, so they didn't so they directly just try to balance the, so make sure they visiting the variable, they didn't accessing the end time instead of login time. That's knowledge we learned it in the binary tree, right? I mean, BST, black red tree, AVL. Those are guaranteed that if we did it the balanced, you will be guaranteed that you will be get login time. If I just continuously put this in this variable, finally possibly I had an end time complexity. So that's it. That's the reason that space of the code. Make sure you will be only difference is performance. Otherwise, I don't need this kind of. I mean, I just only needed to 46 and 47. That should be enough to my continue work. Why I need to add this one? Because of the I'm trying to get this better performance for my accessing the element. So that's a link together. If he's not been don't have a kind of cyclic problem, I can add it, but in this case, I want to get better performance. So that's the reason I have to check it. This is rank is smaller one. So which one is smaller, then I can add it to bigger one. So, I mean, if there is there is a something longer one, there's also a smaller one. Which one should be? I take this smaller subset to add it this further. Okay, that's the things that's the reason S2's now becoming the S1 of the father. That's okay. And S2 becoming the S1 of the parent, and then of course you needed to now your size been updated because it's a little bit size. You can add it to as well as S1 because S1 is of course been extended. Of course, this is union. What's important here is, of course, we need to continue that, right? We already sorted all of the age, right? We sorted all of the age. I mean, sorted with the cost, right? Sorted with the right relationship. Which one is the smaller one? Then we also, we ready to, detected unit cycles, right? If you remember, I have to, based on that, one is I needed to store all of the parents but that one should be, level. I can use this level to when I can add it to join together. So now I'm going to repeat this. Whole cycle. I'm beginning to access from the first one, which is I'm going to access it. I get this first ones to wait. Second one's the X. First, X is destination. Third element is, sorry. First one is first one is a source, and then second one destination. This is weight. But I mean, a little bit maybe confusing where is coming from the such kind of in one object. You just go back to find add age. I mean, when we do the add this age size, I added differences. I add same time the weight. If you remember that when you store this graph, we just only give them starting point and ending point, right? But now I'm same time because I have to concern between the relationship, so that's the reason I same time I give the weight. So should be fine. I mean, count it as one object. So that's the reason I'm trying to extract the three object, right? Then, of course, there is important from the age to x and the 2. It should be not the same, not same. Then I'm going to link together, union, right? Then at that case, I have to, sum it my weight because there's the conditions that make sure my spanning tree is beginning to be selected. Okay, so in the loop, I'm using this condition, using this find as well as unit 2. I'm selecting the, I'm selecting the spanning tree, minimal spanning tree. And then that's the reason each time I have to edit my result. So that's finally, in the condition, of course, in here's, that's my final result. Depend on, of course, the function. Okay, I just give this two of them, two node. One edge of the edge give me the two node, and then the node should be has sub node, maybe has, or doesn't matter. But I needed to check it whether this is should be has and continuously or not, but make sure. So they will be just they give me the best choice that if they had, same parent, what does means? I mean, they have already been linked it before. So that's the reason I'm using this condition to find it. Otherwise, I can able to collect it. Okay. So then I needed to, just print out. So, okay, just I need to run it. All right. Okay, that's they didn't recognize some syntax, which is that, of course, the autos kind of older syntax. They didn't, recognize that. I remember that, of course. So I have the STD. I have to specify the, version of the 17 because I needed to. That's the reason. Okay, now it's working. It's compiled successful. Now I needed to, So that's from 2 to 3. That's the result. 2 to 3. 2 to 3. 0 to 3, and then 0 to 1. That this is the cost is 19th. Okay. Of course, we can. Here's the two things. One's the parent. Okay. One's the parent. One's the parent array. Another is a rank, or you can call it the height or rank. Doesn't matter. Okay. That's important aspect. You need to just follow on the two array. You need to. Let's maybe I can give you a little bit description. If I start from, of course, which one is smaller one? Here's a 1, 2 to 3 is smaller one. So that's the reason 2 to 3. Now I need to give the 2 and the 3. Then I using the find. After that, I have to update the the value of the 3 for 2. I mean, this is further been updated. Then others and the 3's currently is -1. Okay. Oh, no. I mean, 2 is 1. Of course, this 2 is, I mean, 3 is being updated by index of the 3. I mean, index of the 3. And then, of course, rank is because of the, when I updated the increased it, because at the first time is the same. That's the reason they increasing the 2, right? I mean, here. I mean, at the first rank is, this is 1, then also this is 1. Now I added 1 to 1, should be 2, so I can update in the rank array. So that's continuously doing that way. Then finally they can able to collect the what's the useful, yeah, what I needed to find those uncyclic and then not repeated small weighted spanning tree. So that's it being called the minimum spanning tree. So that's the Kruskal is doing. Okay. Now, how about Prisma doing? Okay. Let me start first. That's one of the graph. You can say that this graph using the matrix, storing the matrix, that also you can easily recognize it's what kind of matrix? Diagonal matrix, right? So it's a kind of, you can say that it's a symmetric matrix. It means it's undirected. So if I take care this one side, I can take care the another side. So it should be fine to, should be fine to, I mean, let's take this part as an explanation. I mean, if I take the space of the code here, what I'm thinking is, I mean, from this moment, I mean, here's upper side. There is no way to you can do anything. I can. Okay, I mean, this part, oh, not, okay, fine. I mean, from the diagonal, and then 2, 3, 6, 7, 5, 6, those are which I can concerning as a one matrix. Let's say this one, let's say a 2, I mean, what's the 2's 1, this is 0, this is 1, 1, 2, 0 to 1, right? 0 to 1. And then what's the 3's? 2 to, I mean, 1 to 1 to 1 to what? 1 to 2, right? This is 1, this is a 2. This is 0, 1, 2. 1 to 2. 1 to 2. Hold on a second. 1 to 2. 1 to 2 is 3. And then 0 to 1 is 2. And then this is 0, 1, 2, 4. 4 to 0. 4 to 0 is 6. 4 to 0 is 6, right? This is 6. And then 4 to 1 is 8. 4 to 1 is 8. This is 8. And then this is a 5 to 1. 5 to 1. So 1, 2, 3, 4, 5, right? 5 to 1. There should be 5. 5 to 1 is how much? Is 5, right? 5 to 1 is 5. And then 5 to 1 to 3. 5 to 3. 5 to 3. Where is the 3? I don't have 3. Okay, there is a 3. 5 to 3 is 5 to 3 is 5 to 3 is 7. And then 5 to 1 to 5 to 4. 5 to 4 is what? 9. Okay, that's such kind of graph. And then we need to find the spanning tree. I mean, we're using the prime way. What's a prime? If they will be continuously finding the edge, right? So what they're doing is here, of course, that's starting first. The function, of course, uh, definition. The function is make sure they're finding the minimum weight. What doing is they're trying to find compare the each value they will be beginning the. I mean, at the first minimum is the maximum integer value, so it means everything is not greater than that. So that's the reason I'm comparing all of the vertex, and then as well as the minimum spanning tree set is that we store it whether it's using the visit or unvisit attribute. If it is choose visit, if this fails is unvisit, it means that fails is not visit, as well as the smaller than minimum value means that's we interested. So all the time I needed to find who's next index. Then I using this minimum visit less to skip this if already been visit. That's the reason I using this one, using the K, and also I keep this index. I'm returning back to who's next. Okay, so what it's doing is, of course, I have to remember what's the parent, and then I also store this minimum value. Then this is trying to, avoid repeated excess, which is that visit less. Okay, it is choose visit, not choose not visit. So what it's doing here is at the first it's the initializing step. Give all of them is false on visit. Then all of them is give the all value as a maximum value of the integer. It means so you can beginning to replace with the small value to who's next. Then of course the first step was they give this 0 as a value with the k. Then parent is at the first is -1, which is we try to distinguish who's they has a first do any kind of further parent that does has then continue do it. So actually this is also in time, right? Continuously. From the cycling of all of the vertex. Of course, this is size of the vertex, small one, but I need to start from 0, so that's the reason I'm counting for. And then I found it the most small one, right? I don't know which one, but they found it all of them, because this is minimum is also doing the recursively. If you go back, you can say that's recursively. It's in the 4. It means they will be. Actually, to count it as this is a kind of n square time, right? So possible the n square time, but later on we told about how you can skip the n square time in order to get the minimum value. In order to get the minimum value, if we use the mean heap is, if you remember, mean heap is guaranteed at how much access time? Login time, right? So we can get benefit, not reach the quadratic time complexity. We can decrease the complexity. That's interesting that we can use mean heap to try that. But in this case, not using mean heap. If you're interested, you can access this one. We can later on how we can improve this is another step, but this is very, not optimize the code. So that should be fine to not at the first just storing the in the array, okay, not storing the heap. So that's the array. Next step, when it's finished, when you all is working, then you can replace with the mean heap. That should be fine. So here's what it's doing. What it's doing is this is the if is not empty, then also it has not been visited, then also the age, the age is smaller than that small value, then I can, that's thing, the smaller each step I can get this smaller, age. Then I can edit this age to k, then also that I want. That's we I needed to store in the parent. Then okay, then I can remember the things in the for. So that's the key about my algorithm, depending on the actually visiting or unvisiting. Then also they trying to using the weight as well. So finally they had been already stored. Collect this the parent, so that then I can able to print out those things. Then that's my interested minimum spanning tree. So you can run it, we can run it. Finally, hold on. Can't run it. Why? I think it doesn't. Hold on. It's a problem here. Run again. Yeah, okay. Interesting. So that's as you can see, let's go back to okay, let me make this bigger. Okay. Now, so it means 0 to 1, 0 to 1. No, it's not the same, right? Okay, I remember this is this one, right? 0 to 1, and then 1 to 1 to 1 to 2. Where's 1 to 1 to 2? Okay, then 1 to 4, 1 to 4. So the final is 1 to 4. So you can get the 7. Then this is 9, 16, right? Probably 16, right? So that's a minimum spanning tree using the prime way. Okay, so actually this code is not been optimized. As I can say, the minimum span tree storing in the array, but you can store in the min heap. With you can store, so they can improve the performance better than quadratic time, right? So you can check it by yourself. I give the link, and then you can able to check it. So I think that's the time to make a conclusion. Okay. Okay. So Then we interested in spanning tree. Then the spanning trees, inside the spanning tree, we interested minimum spanning tree, because minimum spanning tree is most useful for us. Then there is a two algorithm existed, the Kruskal and the Prima. Of course, Prima is only applicable in the single graph, and the Kruskal's kind of special, can apply in the not limited only graph, many graph together. It's also fine. Both are come to different kind of philosophy idea. One is the Prima is continuously finding the smallest weight to generating the spanning tree, but I mean, or you can call it the building the spanning tree or discovering the spanning tree. Kruskal is in the other way around. They always believe that finally they can make it connect. So they always concerning a smaller weight. They continuously they connect to who's next. But that's the reason at first you needed to discover all the weight, then sort it. Then sort it means I can each time I can get this, yeah, a minimum one. But as you can see, if you get this minimum one, you can use the mean heap. Then always you can guarantee to get this. You know that, right? Minimal time, login time. Otherwise, because there is a sorting is what, then also finding the minimum wage, it's another one. So we can put together, it's easier to create this quadratic time complexity. Then you can use it one that you can use the mean heap. Then you can able to increase the performance of in the Kruskal, plus mean heap. So yeah, you just need to remember those in the high level. Then plus your practice, then I think you can able to handle and apply in the real case. Okay. So any question?